So let us start from over here. So we'll just recap what we did last time, okay? And so you can start recording, yeah. So recap what we did last time. So I've written down this thing. So recap, if we write the Hamiltonian of this charges plus field, this total system, then the Hamiltonian was basically written like this. So go back and check how we could write it like this. There was the particle part over here, and then there was the field part over here. And of course, if it is a constant of motion, then you have to show that dH dt is equal to 0. We also wrote down the generators, which gives you constants of motion. And you remember these generators come from the total derivatives, okay? So come from this total derivatives because it depends on the endpoint variations. And so when we calculated the generators last time, it contained of 3 parts over here, okay? So the first part came from the delta Ri variation. The second part came from the delta A variation. And the third part came from the time variation, the delta T variation, okay? And so the total generator was written like this. Now, so go back and recall that when we wrote down the Lagrangian again, so this was the Hamiltonian, but previously we wrote down the full Lagrangian. And just for the recap, the Lagrangian was written like this, okay? Lagrangian was written like this, and but again, the first part was the particle part, and the second part was the field part. Okay, so this is what we started. Now, what we want to do right now is talk a little more about energy. Okay, I hope you can see. So if I take this Lagrangian that is right now in front of you and write down the Lagrangian in terms of the Hamiltonian, which is over here, then you will see that we can write it like this. So what we can do, hold on, we can do is we can write down, so take the Hamiltonian, if we write the Lagrangian in terms of the Hamiltonian, then what we have is, I can write down it like this. So my Lagrangian then becomes the first term, okay? So this is how we can write down the Lagrangian in terms of the Hamiltonian. Now, if you look at G, okay, so go back and look at this, look at the generator. You see that in this generator, the variables that are appearing is R, P, E, A, T, right? So in the generator G, in the G, we do not have variables, three variables, do not have the three variables, and those three variables are basically, we do not have v, okay, we do not have phi, and do not have b. Okay. So the generators do not have these three variables. And in some sense, these three variables, what I would call are unnecessary variables. Okay. So these are, in some sense, unnecessary variables, and they do not give rise to any equation of motions. Okay, and so they didn't give equations of motion. So the variables which did not give equations of motions actually did not come in the generators. That's also something that you should keep in mind. Okay. So what I can do now is that I can try to eliminate these three variables. Okay. We already have equations before, consistency equations, which came from these variables, which were the constraint equations, and can try to use those constraint equations to eliminate these three variables, right? So we have other variables which gave us constraints, which gave us constants of the dynamical system, which gave us equations of motion. And then there were these three variables which did not give us any equation of motion. This was only constraint equations. So these are things which is internally should be valid in the system. Now we use those constraints, okay, to remove these three variables. So what we do, so basically we eliminate these variables using constraints. Okay. So what are the constraints? First constraints for the V was basically momentum and the V. So the first one is mi Vi, that is basically Pi minus Qi by C A. All right. So that's the equation of the momentum with both the canonical and the potential momentum taken. Then for the phi, we have basically so E is grad phi, remember, so we can use something like this later. And we also have all of them. So you can use these three equations in the original equation of the Hamiltonian to get rid of those redundant variables. So when we do that, when we do this, then I can rewrite my Hamiltonian. So now we can rewrite H.
So we should actually be using E vector is equal to minus grad phi, right? Why did?
So remember, when you looked at the, go back over here. Let's go back over here. So phi was the redundant variable, right? The constraint equation we got was this, right? So use this constraint equation when we do about the phi.
Okay, okay.
So those three redundant or whatever, unnecessary, superfluous, whatever, you can use any word, they give you these three constraint equations, and we're going to use those three constraint equations to get rid of these variables. So, well, rid of these variables in the sense, we're going to use those three constant equations. Ultimately, we get rid of these variables. So let's see how it goes. So you can rewrite my H. So now,
Sir?
yeah.
Sir?
Yes, tell me.
Yeah, we need to remove these variables, right? Vi, phi, and p.
No, say it again, because sometimes when you guys speak, I get cracked voice, so I don't understand all the time. Say it again.
Yeah, I am saying that we need to remove this variable Vi, phi, and p. Okay.
We want to remove these variables, yes.
Yeah, so we can remove directly Vi from the constant part and p also, but for phi, you are using del dot equals to 4 pi rho, right?
So I'm using the constraint equation that was generated by varying each of these unnecessary variables. Okay, see, unnecessary, I'm saying don't take it very seriously. Unnecessary is not the right choice of word. Variables which did not give you equations of motion, and variables which did not give you some constants of the system. Okay, so I want to get rid of those variables which gave you constraints. Other variables which need not give you constraint. Whenever I have a constraint, I can use those constraint equations. So that's what I'm saying. I'm going to use those constraints equation and see what we get. So let's see what we get. So just one more step. Let me write down what H I get. Then we'll see why I'm doing this. So I want to present you with a fallacy which sort of probably helps you think of how these things are interconnected. So you rewrite this H over here. So at present, we are just using this constraints equation, let's say. So if you rewrite the H, then I can rewrite as, now I'm going to, so here is the H over here, which has the particle part and the wave part. I'm using constraints equation over here, okay? So I'm going to use that to rewrite the H. So use those constraints equation in that H, the previous H. I wish there were some numbers in the equations, but yeah. So then I will have, so this is why blackboards are good. Blackboards, I can have two equations side by side. Unfortunately, over here, I cannot have two equations side by side. So again, I will go back over here. So look over here. I want to get rid of the V over here. I want to get rid of the A, not the A. Which one is there? The phi and the B. Okay. Or want to manipulate those three things. So in this first part, I'm going to put some of this constraint. In the second part, I'm going to put some of this constraint and try to make this equation as slightly less cumbersome than this original equation. So I'm going to simplify this equation. So if you do that, you'll see you'll get what I get is we'll get this kinetic. So the kinetic energy term, which will be Pi minus Qi by C ARI whole squared plus Qi phi Ri, this thing, and then plus dq bar square plus b square by 8 pi minus so now if you look at this equation over here, you will see that the first term, okay, is basically the energy of the particles moving in the field. So this first term is energy of the particles moving in the field, okay, And in the same way, then you can say that the second term, this one over here, is basically the field energy. But if you look a bit more closely, you'll see that this is a bit ambiguous. Okay, so we talk about the energy of the particles moving in the field. There is the kinetic energy part over here. Okay, and then there is the potential energy part. Okay, now the potential energy part is basically the potential energy of the particle in the field. Okay, so in a sense, the potential energy of the particles, okay, this can be attributed to both. Would you call it the potential energy of the particles because it is the potential energy of particles in the field, or will you call it the potential energy of the field, which is over here? So there is, when you have charge and particles in electromagnetic field, it is not always easy to completely, although we started in the Lagrangian by writing down Lagrangian of one part and the Lagrangian of two parts. When you try to associate stuff, it is not always so clear that how you will associate with whether it's this or that. So putting the particle is due to the field. Now I can make it even more complicated or even more fun. So to do that, let us go back to what we wrote in the last class. Remember, when we were trying to get the equations of motion, we're trying to do the minimization of the fields, we had to go from the discrete particle nature or the discrete particle way of looking at position at Ri to a continuous system, right? Where your Qs went to rhos, your Qi, Vi's went to J, okay? So we have to go there. So now you go back to that equation. Let me find that equation over here. Okay. Let me try to find this equation over here. Here, this equation. This equation. Okay. So over here, by suitably defining my charge and the current density with the position of the charges and the motion of the charges, we wrote down this equation, which was this, right? So over here, my Qi phi I, summation over all the i's, gave me my rho phi, right? So this is connected. I can try to use this connection and put it over there because this connection is there. That's how we got the equations. So let me use this connection and go back and simplify the equation a little further. Okay. So use connection between rho phi and sum over Qi phi I Ri. Okay, to simplify. So I simplify this now. This is what I get. Okay, this is what I get. So we have, again, some term which is due to the field and some term which is due to the particles. But something strange has happened over here, right? So you should be immediately saying that this is not right, because I have the energy of the field, I have the kinetic energy of the particle. See, I've only manipulated things that were already there. I've used basically my constraints, and I've used basically the fact that when we went to the Lagrangian formulation over the Lagrangian density, we had to write down everything in terms of density. So we had charge density and current density. This is how we have formulated stuff. So we used those properties and got this Hamiltonian. Just a moment. Hello? Not yet. So see, something strange has happened, right? The scalar potential has disappeared. So now we have an equation for an energy which does not have the scalar potential. But you have always learned from the very beginning, when you started with electrostatics and when you started with everything, the first thing we started this whole series of lectures was writing the energy in terms of the potential, the scalar potential. So the scalar potential has disappeared. So the question is, where is it? Is there some inconsistency over here? Okay. So this is the reason I'm doing this, is to show that you can do manipulations and then you can have and come to some equations which are sometimes inconsistent. But is it inconsistent? Okay. So the answer over here is yes, it has disappeared. But the answer is it is hidden. It is hidden. Okay. So how do I do that? So to show that, it will be a homework for you, but I'm going to tell you how to, I will tell you the hint of how to do it. Okay. So all the homeworks that I'm giving, you must do it. Okay. Every day I give you a few homeworks and you must do it. So you take the Lagrangian, okay. So this is the Hamiltonian that I have now, right, with all the manipulations. The manipulations are all valid manipulations, okay. It's not that I have done some invalid manipulations. So there's no trick in that, okay. So I have this Hamiltonian, and the Lagrangian, remember, was written in terms of the Hamiltonian. The Lagrangian was, again, to write down pi dot dri dt minus 1 by 4 pi c, then there's integral over dqr, okay, and e dot del a del t minus h. This was the Lagrangian in terms of the Hamiltonian. So I can input this Hamiltonian over here now. So I can take this Hamiltonian and put it over here, okay, to get a new Lagrangian. So that will give me a new Lagrangian. So this gives you L, I don't know, let me call it L nu. Something like that. That's very bad notation. Or L simplified. Let's not call L nu. It's called L simple. So your homework is, this is your homework. Okay. Vary, okay. Vary the action using L simple with respect to this is the homework. And I'll give you the answer, what happens. When you vary this action, okay, over here, so you go back and you vary this action with L simple, you will find that if I have to vary this action, and then of course, what I want to find out is basically just for this E part, okay? So everything will have a delta L. So delta L due to the variation of E. That delta L, you will find, will come out to be minus 1 by 4 pi C. There will be a d cubed R, okay? So obviously the first part and the last part over here, first part will not, it will go to 0. The last part will have some contributions. So last part, remember, will have to vary. And this middle part will be there. And so this will give you delta E. Handwriting is becoming really, really bad. Delta E dot 1 by C del A del T. Yeah, this C has to go over here. This C should go over here. Plus E. This is what we will get. And this, of course, has to go to 0 if I want the variation to go to 0. So what does that mean? If I do exactly the way we have done before, it would mean, so this would imply, what would this imply? This would imply that my E is equal to minus 1 by C del A del T. But this is something that again is contradictory. Your E cannot be minus 1 by C del A del T. When there is no time variation, E is grad phi. There has to be a grad phi over here. So phi is missing over here also. So what is happening? What is happening is all these manipulations and things that I'm doing right now today. What happened over here? Why is this not right? What is hidden that we forgot to take into account? Okay. To get this, remember, what is your primary requirement? Our primary requirement is that delta E is arbitrary, right? So this whole part is equal to 0. I can only equate the second part, this 1 by C del A del T plus E equal to 0, if the first part, delta E, is arbitrary. So for any arbitrary delta E, if this whole thing is equal to 0, then this 1 by C del A del T plus E should be equal to 0. Right? But is it arbitrary? Over here, it is not arbitrary. Why? So over here, but it is not. It is not arbitrary. Why is it not arbitrary? Because remember, when we did, initially when we were doing the Lagrangian formulations, at that time the delta U was arbitrary. But over here it is not. Because to arrive at the Hamiltonian which gave the L simple, okay, what did you do? We used constraints. Okay. So we have used the constraint, and that thing, although we are not seeing it over here, that thing must remain. So what constraint did we use? We used this constraint. We use that is 4 pi rho. So now, because this constraint is used, if I vary this, so this basically means that this E must, excuse me, also obey. So if I take a vary this, also obey this. So for any given charge density, this was the case. So this has to be 0. Right. So this basically means that this delta E arbitrary is not true because it also has to satisfy this thing. Okay. So we want this vector in the bracket, this vector in this bracket. Okay. This vector in this bracket, we want that vector into bracket, which is multiplying delta E. So now if I want to satisfy this equation and this equation,
sir,
yes.
how do you wrote the last equation?
I just varied it. Just take a derivative of this. Small.
Okay, you applied this constraint equation.
Yeah, this is a constant equation. This is a constant equation which is there, which you had used to get the H, remember? So initially, when the initial Lagrangian, which we did 2 classes before, or last class, whatever, at that time there was, because delta E was, the constant equation came out of variation of the Lagrangian. And the Hamiltonian came after that. But now we have used those constants equation to eliminate variables. But the constants equations are there. And when you have done that, we have no more. What basically shows that when you have done that thing manipulation, you no more have the arbitrariness of the remaining variables. The remaining variables have coupled, and the couple is hidden inside it. That's what I'm trying to say. So this constant equation is there. And if you vary that constant equation, just take the small variation of that. Rho is constant because rho is for some charge density you're doing it. So then this is 0. So if I have this, and over here, remember this, so delta E times some vector, okay, some vector which is in the bracket, okay, over here. So this is some vector in the bracket. So let me call this some vector. Okay. So this is some vector in the bracket, okay. And over here, so it basically tells you that if you look at whatever that is vector that is in the bracket, which is multiplying delta E, that vector must be a gradient of a scalar, because otherwise we do not get this last equation. Okay. So to satisfy the constraint equation and this delta L equation, and delta L equal to 0. The vector multiplying delta E in the delta L equation, this vector must be a gradient of a scalar. Okay. That basically means I will have my 1 by C, this thing, okay? So my 1 by C del A del T plus E, this has to be a gradient of a scalar. Okay. So if this happens, then we can go back and write down my delta L so that it is consistent. So with this, we can write down a consistent delta L, because then what I can do is I can write down, so basically do the 1 or 2 lines I'm skipping in between. It's very simple. Write down, then you can write down delta L can be written down as R so this scalar potential still there. Okay. So the whole point of this exercise was that when we manipulate and something becomes simple, you have to be careful when you want to go ahead with it. Okay, because seemingly unphysical or unreasonable answers we can get, and that's because in doing this manipulation we have used some equations which we have forgotten later, and then our assumptions later may not be valid. So this was an example which showed that this independence of delta E, that is arbitrary, that was not valid, because in getting the Hamiltonian itself and then from there to the Lagrangian, we had used constraint equation, and that constraint equation actually couples your delta E with something else. So it's not completely independent. We have to be careful that the delta E goes to this rho and phi and these things together. So one thing, again, I would like you to do over here is prove this. So first of all, go through the lectures, go through it slowly, go through these equations slowly. Sometimes when during the lectures, it may not always be clear, because it's very difficult to follow all these equations as I scroll up and down. But go through these lectures is to write it down. By the way, I have put the first everything that I've written there. I have put it in the Moodle, so it's there now. The Moodle. Okay. So prove that total energy is conserved. That is, this is something that I asked you before. So over here, your H is half mi vi squared plus this H. SHOW. So go over here, take derivatives from over here, and try to prove that this is conserved. Okay. Another one. So by now I have given you at least 10 or 12 things to do for your homework. Okay. This weekend I'm going to compile all of these, and I'll ask the graders Anuma and Oritra to help me and compile all this homework and submit to you as the first homework assignment. Okay. You should do this thing. Today I will not start anything new after this. So next day, what I plan to do is go to the next stage of this Lagrangian stuff and talk about invariances. Okay, conserved quantities and invariances and things like that in this kind of formulation. Okay, but that will not start today. Today, what I plan to do is that in the half an hour that I have, or maybe 40 minutes that we have. So how many students are here right now? 21. Okay, good. So 19 of you, I guess. For people who have not given the drop test, okay, and for people who have given the drop test also, for them it will be easy. I would like to pose you with 2 questions. Okay. So there was this comment about vectors over here. So let me just write. So it is there in the Moodle page also. If you can access your Moodle, there are 2 problems that I would like you to try out now. It's easy problems. Okay. So please try these 2 problems and email all 3 of us the answers. Okay. The first problem is this. I have basically given an electric field and a magnetic field, and these are in 2 frames. Although we have not done relativity right now, but for this you don't need to know relativity. These are in 2 frames, and in one frame it is EB, other frame it is prime, and I've given you the relationship between these. You basically have to show that if in one frame the E and B satisfies source-free Maxwell's equation, and it's very important that it is source-free, then in the other frame the E and B also satisfies this Maxwell's equation. And then comment a bit about the implication of this result for source-free Maxwell's equation and E and B are everywhere perpendicular. Okay. So that's one problem. So you can have a look at this. And the other problem is something that I've given you already to consider. Hopefully, if you have followed all those things that we have done in the last few classes, then you should be able to do this. So I have this electromagnetic field, Lagrangian, which is a particle and the field. The particle Lagrangian I derived. The field Lagrangian I just wrote down. I want you to justify that the form of the field Lagrangian is what I wrote over here. Okay. So for this, you only need whatever you have learned in your ED1 or basic ED. So from there, find out and justify that the field Lagrangian is this. So you have like half an hour, 40 minutes to do this. It should not take more than that. Please go ahead. And if you want to see both these problems together, it is there in the Moodle. Okay. So you have to do this and send it to me and Anuma and Oritra, whatever, 3 of us. Email me. Okay. And please email me whatever you can do in the next half an hour, 45 minutes. Don't take more than that. Okay. So good. If you have any questions about this, you can ask me.
Sir, for the second part. Second question.
Second question, yes.
Yeah, we can directly prove that it satisfies all the equation and constant equation directly varying that. Is that
No,
fine?
which one? This one, question number 2?
Yeah.
See, question number 2, this is the Lagrangian density of the field, right? Just show
Yes, sir.
that it is a Lagrangian density. This formula, where does it come from? It cannot come from just like that, right? You have to find out that you can write down the Lagrangian density like this. That's what you have to show.
Okay, you are saying that some physical argument that it is the Lagrangian density or something.
No, not an argument. Derive this formula. Get this formula from first principle. Simple 3-4 line exercise.
Okay. You are saying that we can directly use the equation of motions, and from that we can get this.
No. From Lagrangian, you get equation of motion.
Yeah, we can also go reverse.
No, that's not the way to do it. If I want to ask you to write down the Lagrangian of something, suppose you have some field equation, you want to do some field theory. You want to write down the Lagrangian of that field theory. Okay. Something, these are fields, E and B are fields, right? You write down the Lagrangian of the field theory. It's not written in 4-vector form, but suppose you want to write some field which is not in 4-vector form. How do you write down the Lagrangian? What is a Lagrangian? It's very simple. How do you get the Lagrangian of the particle part?
Yeah, particle part also we get from because first we know the equation and we can reverse it trace back.
We don't do that. Go and see how we wrote down the Lagrangian of, how do you write down the Lagrangian of a particle moving in a potential for the simple example that we did. When we did
Yeah,
that, what is
come out to T minus V. That's
Yeah. So try to do that, T minus V. Lagrangian is T minus V. I have given you, I've basically told you. Show that if you do T minus V for fields, you'll get it. So what is the kinetic energy? What is the potential energy? You have to write down and then write this. Try it out. I mean, obviously,
Sir, a doubt about homework. We have to submit it on Saturday.
This is not homework. This is now.
No, not that that you are saying that I have given you 10.
No, homework I will give you on Saturday. You will have 2 weeks to submit.
Okay, fine.
Always homeworks have 2 weeks to submit, typically.
Sir, I can't download the second quiz PDF version that is given in the Moodle.
Cannot download it. Why? Let's see.
I can download it.
Others can download it.
Yes, at least I can.
So then it can be downloaded. Otherwise, I'm going to show this again. Hold on, let me share it again. The sharing will, if I don't use my Blackboard, the sharing goes away. So that's one problem. This part you don't even have to download. This is what you have done in your notes before. Okay, if you have written it down at all. And the reason I am writing it so that you can also write it just like in class. Otherwise, I can just show you pre-written things. Okay, that will be much less of my effort. Writing it down in the class has much more effort, right? It makes things slower. Otherwise, I can go very fast and just show you pre-written equations and just talk about it. And then this one is the other one. Question is, have everyone been able to get these 2 questions?
Sir, can you just scroll down in the second question?
Sir, in the first question, the parameter theta, is it a constant or it's a space-time dependent quantity?
Which one?
In the first question.
Yeah, what is constant?
No, what I'm saying is the parameter theta, is it constant or is it space-time dependent?
Constant theta.
Okay.
Simple, simple, no complications. Just want to say for people over here, these two problems were there in the drop test. So people who have given the drop test, they may have already done it. If they have done it, they can do it in 15 minutes of both these problems. Just quickly, I want to again ask you, have people been able to get the problems from the Moodle, or is there anyone who has not got it yet? So everyone has got it from the Moodle. So if there is anyone who has not been able to download it from the Moodle, please let me know. Okay, very well then. So I'll wait for your emails to come in some time. Okay, I will switch off my video because there's no need for the video. Aritro, Onoma, you can stop the recording. Okay, because now I'm not doing anything. But please don't start working on this for till 2 o'clock. You know, whatever you can do in 30 minutes, I think is more than enough. So best of luck. Hope to get your answers very soon. I'll stop the video.